Thank you very much. And I really appreciate the invitation and such a concise introduction. So well done. Um, it's a bit trepidatious that I present today's talk because it's kind of a core aspect of what STRN and NEST do. It's all about the speed or the temporality of energy transitions. And I think, continuity and change and temporality and temporal dynamics are probably evident in every single transition. So in a way, I'm kind of like going into the lion's den with my perspectives on it. I think it's always good to start, I do this with my students by kind of unpacking some very recent data that kind of gives the impression that we're in the middle of a great rapid transition in some of the energy and mobility devices that we use. So these are the latest numbers from the International Energy Agency, and it looks fantastic. We're jumping from 200 gigawatts of solar and wind to more than 1,000, right? So it's almost a quintupling of renewable energy in your lifetime, in the next decade. So this is like not mid-century or end of century. It's literally while we are living and breathing in the next 7 years and 8 years. And look at the number of electric car sales as well, jumping from 3 million in 2020 to 58 million. And you could even go further and take it up to 2050, and they jump up to about 1 billion, 985 million to be precise. And to put this in perspective, we only had 1 million in 2015. So again, in your generation, we could see growth in EVs from 1 million to 1,000 million. And finally, you can see hidden transitions in the home and in our factories and commercial offices, where we continue to do transitions in how we harness energy and convert it into useful fuels and services, things like insulation, double glazing windows, and energy audits and retrofits, and a whole variety of other things that help actually reduce energy intensity. I like this number just because it shows how the kind of global proliferation of EVs is not only on a kind of upward trend, it also shows the number of years it took to reach 1 million keeps shortening. So it took like 11 years to sell the first 1 million battery electric vehicles, and then it was about 3 years for the next million, then it was about 1 year for the next million, now it's about 1 million every 3 months. So again, acceleration of transitions and the diffusion of these types of devices. And you can see as well, it's not only markets like the United States. China is by far the world leader. And you also see a lot of kind of non-Eurocentric countries in these diffusion trends as well. So it's not just the global north, right? India, China have very large numbers of scooters and e-bikes and other forms of electric mobility. Speaking of the global south, you also see projections that I don't believe, because they're meant to be inspiring, the projections that we could also see universal energy access achieved by the end of this decade. Now, that does require us to kind of meet our sustainable development goals. These are just forecasts. So anyone who knows about the political economy of grid electrification would know that these rarely actually happen because there's too many barriers and obstacles. But at least it also implies that we could see another rapid transition in this decade with roughly 900 million people accessing new forms of modern energy around the world, almost exclusively in the Asia Pacific, Sub-Saharan Africa, and parts of Latin America and the Caribbean. However, are these really transitions, or are they simply additions? And this is just showing you data plotted in two ways. I think the left is the United States and the right is the globe. And again, it just shows that when you zoom out to the kind of global scale of total primary energy supply, it doesn't look so good. It looks like we're just kind of adding thin layers of EVs and solar on top of an already very dominant fossil fuel regime. And so this kind of acceleration looks fast because it's happening from very small starting points. But to shift major global systems, they may have too much inertia or path dependence or momentum. And I think that gets us into the topic of this presentation. How fast are energy transitions, and what are they? As Aristotle said, many years ago, those who control the definition control the debate. So how you define an energy transition will intimately shape what parameters you think are important, whether it's energy transition 1.0 or 2.0 or 3.0. And as you all know, you could put 20 academics together and get 25 different definitions. Even I have not defined energy transitions consistently in my own career. You have the traditional notion that it's changes in supply. So nuclear substitutes for gas, and wind substitutes for coal, energy efficiency maybe substitutes for biomass. You can also shift the technologies that use energy, steam engines, internal combustion engines, gas turbines, light bulbs, mobile phones. You can also change markets that don't have anything to do with technology. There's been a global shift from monopoly markets for electricity and energy to restructured, privatized, and liberalized markets. These are just changing the rules about how tariffs are set, about how you unbundle assets, transmission, generation, distribution, how you allocate costs, and how much profit you allow entities on those markets to subsume. And you also have a whole school of work in diffusion studies, talking about early adopters and late adopters and how long it takes particular innovations to reach saturation or to at least reach major shares of a market. And of course, you can also ask about any four of these changes, right? In supply, in demand, in regulation, in diffusion trajectories within homes at any scale. At the scale of a university, at the scale of a country, at the scale of the globe. And that will also greatly shape how fast or slow you think transitions are happening. There is no shortage of heuristics or conceptual devices in the energy transitions field. I quite like Grubler and Charlie Wilson. They have this kind of neat spatial temporal model. They didn't name it. Maybe they should have. They didn't give it a name. But it basically says that major energy transitions historically kind of go through phases. So they start with kind of experimentation and tinkering, and then they scale up to units, then they scale up to manufacturing economies of scale, and then eventually they reach market saturation. And they also have a spatial element. These innovations, like Watt's steam engine, begin in England and then phase out to Wales and Scotland, and then phase out further across the English Channel to France and the rest of Europe. My own proclivity as a scholar, my own PhD, used another one called Large Technical Systems, which is Thomas Hughes, who's famously known to create kind of the notion of a seamless web. So large-scale energy systems, bind together political, social, technical, cultural elements in a single system that gets momentum, which is kind of like path dependence. And Hughes also talked about how he thought these large transitions go through phases. In his work, which was 1880 to 1930, electric utility systems in Western Europe and the US, he ended it with style. And so we recently built on this work to then kind of say, well, what happens after style? You actually have other phases like reconfiguration or contestation or even decline and stagnation as pressures destabilize certain things. And while Hughes made his mostly a linear model, we tried to put multiple arrows in here to kind of indicate feedback loops and how you can actually, systems can go backwards and forwards. And while Hughes only looked at electricity, we also found that, these types of phases of transitions at the large scale affected multiple technologies: railways, telecom, pipelines, sewers, gas systems, electric streetcars, coal, French railways. Which then, of course, begs the question, all right, you've got Grubler and Wilson and you've got Hughes. Well, how many different technical theories might we have? And here, we thought it would be kind of cool to survey some of the theorists. So we wrote to people like Frank Hills and Johann Schott and others who were kind of theorizing different conceptual devices for socio-technical change. And we only interviewed 35 people and got 96 theories, which is far more than 3 theories per person. And they're also from a rich domain of disciplines. It's not just innovation studies and science and technology studies. You've got behavioral science and history and economics and political science and transport studies and gender. And we have a long list of an appendix that gives you all 96 theories in alphabetical order by discipline, by name, who the key authors are, and how it seeks to explain socio-technical change, which is a proxy for transitions, because you're talking about how people adopt a new kind of socio-technical technology or behavioral practice over an old one. And in this really long article, we also shortlisted 14 theories, which were they were the most frequently mentioned. So this is kind of like expert consensus, because the question we asked was, what theories are most useful at explaining socio-technical change? And so we have these 14. Our experts seem to agree that they were the most useful. And some, look at the top, right? We only had 35, and we've got 43% of people saying it's the MLP, and 40% of people saying it's social practice theory. So clearly a repertoire of conceptual devices that we can use to try to explain, predict, and examine energy transitions. So moving away from this quagmire, what about some of the empirical elements of transitions? And so if you go back, this is Wilson and Grubler already, but this time I've circled things in red. You can see, well, their kind of heuristic reveals that these transitions take a heck of a long time. I mean, in the upper right, even though we're phasing in coal, which had a lot of advantages over animate power and kind of, old school windmills, it still took a century, right? 96 years was the kind of fastest. And more recently, even though like electricity and modern liquid petroleum have immense benefits as well, they also took half a century to kind of phase in. And these numbers convince people like Václav Smil, who's a geographer, to kind of say that, well, this means, according to him, transitions have been and will be inherently prolonged affairs that are impossible to accelerate. Not difficult. He went all the way. Impossible to accelerate, even if we were to resort to highly effective interventions like carbon taxes or coal phase outs. And this plots the same data from Smil twice. And so the top is the timeline, but it's hard to add up the numbers. So the bottom just shows you how long it took. And this says, well, at the global scale, it took coal 118 years just to reach 25% of total primary energy supply. Oil, 80 years, natural gas is 91. Nuclear, wind, solar aren't even close to the 25% share because we're talking total primary energy. We're not talking just electricity. And then if you switch the lens a little bit to talk about diffusion, Arnolf and Charlie and Greg have this really nice piece that kind of looks at how long it took us to invent in the formative phases, different end-use devices that use energy, like, gas turbines and motorcycles and jet aircraft. And then on the right, you also see, well, how long it then took after we completed the formative phase to actually diffuse them to the market, to commercialize them. So the kind of true diffusion phase is both added together. And you can see, some of these technologies took multiple centuries. And even the fastest ones, when you add them both up, still took 30, 40, 50 years because it takes a long time to form and perfect and invent a new system. And what's worse, this is just for individual devices, or if you like STS, technological artifacts. It gets even more difficult when you talk about system transition or systems of systems. It's far easier to replace a combined cycle turbine than it is to replace an entire grid, which has vertically and horizontally integrated coal mines, gas wells, pipelines, transmission and distribution infrastructure, transformers and pylons, spent fuel cask storage facilities, and a whole variety of other SCADA systems that are built into the grid. So systems transitions are magnitudes of order more difficult, according to Grubler, Wilson, and Emmett. The final thing I like is you can look at it the other way. And that's not how long it takes to phase something in, but how long it takes to phase something out. And here, Bruno and Frank have a fantastic history of UK coal, which they rightly call the flip side of energy transitions. And you can see that, it also takes an equally long time, even though the UK knew they wanted to phase out of coal in the 1950s because of the Clean Air Act and the huge smog in London that choked and killed people. They sold London fog coats, not because of actual clouds, but because of pollution and smoke. Even though all of that, even though Margaret Thatcher made it her mission to dismantle the coal lobbies and unions in the 80s, it still kind of hung on there. So you can see how long it took to destabilize just one technology in a regime that's been trying to get rid of it for 50 or 60 years. You can also see how uncertain those changes are. It's punctuated equilibrium. It's not a flat line or an S-curve, right? It's a very disjointed staircase that looks, like a roller coaster, which also shows you how nonlinear these types of phase-out things can also occur in practice. Now, there are some peculiarities, though, when you talk about this kind of case. These transitions are really long. It's pretty arbitrary at what point people say there's a transition. They tend to be nice round numbers too, 5, 10, 25. Why not 28.8? Right? Why do we have these kind of nice even numbers at which point we say a transition occurs? Hardly anyone does look at whole systems and systems. They still tend to look at bikes or EVs. I mean, Weeby Biker, right, has a whole book about bags, bulbs, bake lights, and bicycles, 3 artifacts. But these tend to look at isolated technologies, not how systems co-evolve. And I can give you 2 really interesting examples here. Internal combustion engine cars at the turn of the last century competed with EVs and actually cannibalized or mimicked many of their innovations. pneumatic tires, electric starters, larger boot spaces, yeah, even windshield wipers actually first appeared on an electric vehicle. So is it really right to say that the internal combustion car won when actually it was kind of hybrid, as many of these other features from EVs that became incorporated into its design? If you only focus on the internal combustion car, you miss that dynamism. Or you also miss here how certain systems kind of co-evolve and supply, push, and demand pull each other. The classic example is railways and telegraphs, because you were using the same labor sources and you were also usually laying telegraph along the rail line as a communication device. So they tended to kind of couple together when you deployed them. The technologies, the labor, and the financing tended to be consolidated. You see a similar symbiosis between roads and oil. As oil gets more refined, higher octane gasoline is used, then people have a demand for more roads. But as there's easier roads, people then have a demand for more oil. So we really have a kind of poor job capturing the co-evolutionary dynamics of these system transitions in most of the literature, with a few exceptions of scholars who are taking up that mantle. And you can see why it's very hard, right, to do multi-systems analysis, given the messiness of data, the complexity of systems, and the fact that a lot of these socio-technical systems are so big, it's very difficult to determine where they end. One of the scholars in STS even called this epistemological chicken, because you keep expanding the lens by what your theoretical devices cover until everything is included, right? And for those of you that like the MLP, it's the landscape, right? Even Frank Hales is called the landscape is the garbage can for what doesn't fit in any of the niches and regimes, right? So we kind of see this expansion of conceptualization to kind of cover the entire environment. And finally, there's a question about your unit of analysis, getting back to this notion of definitions in Aristotle. Are we talking about, you know, oil as a whole, or much smaller, faster changes in internal combustion engines, oil lamps, boilers, furnaces, et cetera? Because those, even though the big transition to oil was taking a long time and it looks slow, some of these individual transitions were extremely fast, with 100, 200, 500% growth per year. So again, looks fast at one level of analysis, looks slow at another. And that's where I've made my meager contribution to the transitions literature by kind of, well, looking for extreme cases of transitions. Can we find cases where you do see rapid changes in end-use devices or rapid changes in national supply? And if you look hard enough, again, they're not representative cases, they're extreme cases. You do see them. And in fact, you do see them in our lifetime, most of us. These have all happened in the last 50 years. I'm almost 50. You can see how fast some of them took, right? Some of them achieved a 25% market share in 1 year, 2 years, 3 years. And then you can see on the right how many people they affected. And those numbers are small on this table, but they're actually really big in practice, because those 10 transitions affected 960 million people. It's almost 1 billion people have changed the way that they consume or use energy rapidly in our past 50 years, with the biggest transitions being cook stoves in China, cook stoves in Indonesia, air conditioning in the United States, and then that's nuclear electricity in France. And we replicated this, funded by a Horizon 2020 grant, to look at heat decarbonization, and found the same thing. We also looked at 4 other heat transitions, which were not just rapid, they were also deep. And again, these affect another 310 million people. And these are actually even more recent, right? With examples like Finnish heat pumps and Chinese solar thermal happening even, you know, the last decade is when they're kind of ending. And then you have colleagues, STRN colleagues of mine, like Florian and Carolyn, who argue that the kind of fundamental drivers of transitions are changing. Historical transitions tended to be by accident or crisis. And they're saying, well, going forward, you know, we can do experiments, we can kind of do transdisciplinary work, we can do policy learning, policy mixes, we can plan for these things. Hurrah, right? We can actively govern new transitions in ways that planners never would have even thought of 50 or 60 years ago. We can see these complex technological innovation systems and ecosystems of innovation coupled together in very unpredictable ways. The good example here is the failure of German industrial strategy to catalyze solar energy with their feed-in tariff. It worked, but just not the way they thought. It worked by stimulating Chinese manufacturing, which then undercut German industrial strategy. Now, this was good, arguably, right? for the diffusion of global solar photovoltaics, but it was very bad for the Germans. It was never their intent with their feed-in tariff, and how they really hoped to kind of catalyze solar manufacturing in Eastern Germany. But it definitely accelerated solar adoption and manufacturing in ways that hardly anyone predicted, in the same way that also we didn't do a good job predicting shale gas. And finally, Carolina and Florian were also very positive about the Paris Accord, and at least kind of noting that at least for the first time, unlike Kyoto, we have a global commitment to move towards decarbonization that is mostly abided by. The United States is now back. And it is, being treated seriously with nationally determined contributions and emissions budgets, and most countries are roughly on track, to implement those. Florian and Carolina and Paula have also talked about how we have new policy tools. Now, just like Bruno and Frank talked about the phase out of coal, we now have policies that can stimulate this phase out. And a whole basket of policies that can ban cars and incandescent light bulbs and coal. And you can change market rules or implement control abatement or ensure balanced debate, which kind of delegitimizes certain things, like perhaps blue hydrogen at the moment is currently suffering a bout of legitimacy as people are questioning whether gas, is it as bad as coal or not? Well, it depends. And so I think this is also quite useful because it kind of gives you another side of policy that's beyond just supply push or demand pull. You can phase out. And I like this report, not because I think it's particularly rigorous, but because who did it? This is from Citibank. And they were predicting a decade ago the end of oil. And they were kind of arguing, well, for the past 60 years, we were obsessing over kind of peak supply of oil, NP Hubbard and its oil peak in 1973. But in fact, the true peak for oil won't be a peak in supply, it'll be peak in demand. In the same way the Stone Age didn't end for lack of stone, they're kind of arguing, well, we have better substitutes for oil, in this case, shale gas, which is now substituting for shipping, power generation, chemicals, and a whole variety of other things that are called a flattening of oil demand. And the final thing I wanted to say before I kind of wind it up is the kind of perspective of energy incumbents and utilities also implies that they see extremely rapid transitions that they also view as threatening. And so here, I'm going to borrow from some slides that aren't mine. I had the privilege of attending this JUNC coalition. I should have renamed it. Global Intelligent Utility Network Coalition, which was run by IBM, and it includes some of the biggest electric utilities you probably know, including TEPCO. They brought you Fukushima, but others like Ørsted, Dong Energy, and Duke, and Encore, and SGGE, and Tata. And there I was quite shocked that, for these types of utilities, the energy transition is not academic, it's not historical, it is happening right now and greatly disrupting their markets. And this is just showing you, this is from Centerpoint Energy, all of the disruptive technologies that they're scared about, right? That are kind of eroding their demand. I mean, you can tell it's an incumbent slide when rather than call it solar democracy, they say PV grid defection. People are defecting from their grid, which is also known as self-sufficiency and prosuming. And I think it was very telling that some of these energy companies are so paralyzed with what they're going to do that they're even proposing new business models that have nothing to do with energy. So I had to stop myself from chuckling that one of the utilities got up there and said, well, you know what? Even if we stop selling electricity or gas, we can sell data. We can do data analytics. We can be a bank and offer financing and green bonds. Or we can do market analytics like an Elsevier, right? Or a Bloomberg. And so it's quite interesting that like very few of these business models actually involve cubic meters of gas, right? Or tons of coal or separated work units of uranium or kilowatt hours. And this is the last slide from JUNC. And this shows you back then in 2015, this is from the utility in Houston, Texas, the 67 different apps that were making homes smarter, more efficient, more easy to control, more convenient. Many of which involve energy, lighting, heat, right, general solutions. And many of these could actually substantially change, right, domestic practices and how we put energy prices to use. And what we had a lot of fun. I really liked this slide. I was so inspired by this. I wrote a grant proposal that somehow got funded to actually ask the question, well, how many of them are in Europe? So we repeated this 2 years ago. And we conducted 31 expert interviews with smart home adopting experts, and we did 37 site visits all across parts of the UK to kind of see what smart home technologies are on the market. And just as an aside, it was 67 in Houston in 2015, and in 2020, it was 267 available. And you can see here, again, look at how energy dominates: lighting, energy gas utilities, integrated solutions, which is where you've got Nest and Hive. But also, you have 50 Fortune 500 companies involved in this space. These are not new entrants or lightweights. These are some of the biggest companies like Apple, which is now number 2. Saudi Aramco just overtook them. But these are Google, Microsoft. These are Nike companies that that are extremely competitive. So it does imply, again, very rapid changes in how we use energy and other things in the home. And for those of you that are a bit older like me, I still remember when there was no internet. 1992, 1993, it was blackboards, and you had a modem that made noise, and you used Netscape, and it was really slow. So the fact that we would think through, in 1995, I never would have imagined that in 2015, we have a smartphone that has an internet connection that manages apps, right? And so this is just 30 years. Look how much we couldn't even have anticipated, perhaps, the way in which we can visualize, control, monitor, and automate different energy devices in the home. So again, it kind of speaks to, like, in just a very short amount of time, the rapidity of certain types of socio-technical change. Okay. Last thing I wanted to do, since I've got 5 minutes left, is take another step back, since this is Nest, and kind of talk about a final element of transitions work that I like. And that is why I really believe scholarship on transitions needs to be multi and interdisciplinary. And I'll explain what that means. I think that the topic of transitions needs to be multidisciplinary for 4 reasons. The first one is hidden in this slide from Felix Kreutzig and colleagues who are writing about demand reduction. And I really like this framework. It's called the Avoid, Shift, Improve framework. So they're kind of saying, if you want to decarbonize and get carbon out of our our economies, you can't just improve technology. You also need to shift patterns of modal use and avoid and phase out, right, things you don't want. So you have to do all 3 to stimulate a fast transition. But the reason it really requires interdisciplinary thinking is because look at the table, right? You've got to get a handle on mobility and transport. That's transport studies and geography. You got to get a handle on buildings. That's architecture, built environment, demography, sociology. You got to handle industry. That's industrial manufacturing, industrial ecology, advanced manufacturing business models and supply chain management. And you got to get a handle on food, which is anthropology, ethnology, nutritional sciences, life sciences. So I've just named like 12 disciplines that have to work together to get you a potential framework that illustrates how Avoid, Shift can improve, can add in different sectors. Second reason relates to those earlier slides I was showing about universal energy access and the fact that we still have, 800 million people who have never seen an electric light bulb, or tasted a cold beer in their home, or sent an email because they're in extreme energy poverty. And this energy poverty also means that a lot of them cook with solid fuels, and these solid fuels that you use inside the home create, it's like living in a giant cigarette. And so this has led some, like the Global Alliance for Clean Cook Stoves, to talk about how, like, the most dangerous thing a woman can do is actually cook in her home. And it actually causes about 4 million premature deaths per year, which is far more than many other, it's far more than malaria, tuberculosis, and HIV/AIDS by 2030. But if we're going to solve this type of transition, the World Health Organization is telling us we also need a very interdisciplinary approach. We need the kind of fuel science, combustion science people to, like, build us better sources of stoves and better fuels, so fuel science, engineering. We need those sociologists and architects and building designers to also change habitats and change people's homes so they have ventilation and they have better replacement and better, kind of technology in the house, domestication. And then finally, we need social scientists like sociologists and anthropologists and ethnographers to also change user practices with how they dry fuel and how they actually conserve heat and the times that they cook and whether they cook with their children or not. So again, you need all 3. You need an interdisciplinary approach that harnesses the fuel sciences, the built environment, and user behavior. I have two more examples, believe it or not. This is the multi-level perspective designed by Frank Hales, Johann Schad, and others. And the idea here is that, new innovations, which are niches, have to evolve and compete against regimes, and they are shaped by the broader landscape. So it's a kind of multi-scalar framework, multiple levels at the same time. And it is a temporal one, right, that goes through phases like acceleration, stabilization, decline, as well as these kind of windows of opportunity. To get a handle on the MLP, though, which is pretty well developed, look in the left. You have to be able to understand new technologies, so that's engineering, but also business models, that's business studies, and also behavior, that's psychology. You have to understand industry, that's industrial studies, culture, that's media studies, policy, that's political science, user preferences, which is, I guess, grounded research. And you also have to understand broader changes in demography, economic shocks, etc. So again, if you're going to actually understand the multidimensionality of transitions processes, you need about 30 to 40 different disciplines working together in concert. And the final example deals with ethics and justice, which is a kind of topic that's close to my own heart, where we've done work looking at vulnerability, dispossession, and injustice in energy transitions. We've taken 4 transitions that everyone knew a lot about: French nuclear power, German solar energy, battery electric vehicles in Norway, and smart meters for gas and electricity in Great Britain with in-home displays. And one of the questions we asked across our mixed methods research design was what injustices occur around the world, and it turns out a lot of them do. So even though our study was at 4 European transitions, everywhere in red is a place that was negatively impacted, according to our respondents, by these transitions, like interrupting tar sands viability in Canada, and diminished coal exports for Peabody Coal in the US, and reliance on hazardous lithium mines in South America, and extraction of cobalt and copper from the Democratic Republic of the Congo, and interruption of LNG exports in Australia, and reliance on slave labor and forced labor in China, and it goes on and on. And some of these can be quite severe, like this artisanal miner for cobalt, who is so poor, if you see, he doesn't even have shoes. He took off his flip-flops. And what I find striking about this is also what's not in the book. He doesn't have a shovel. He doesn't have a ladder. He doesn't have lights other than a small headlamp. He doesn't have any structural support. He doesn't even have steps. He's just like kind of crawling down into the dirt. And he doesn't have any adequate ventilation, PPE, or medical equipment. And yet we need such cobalt and copper intimately for things like electric vehicles, solar cells, energy storage, hydrogen fuel cells, small modular reactors, lightweight vehicle production, and a whole variety of other eco-innovations that we hope will help us fight fuel poverty. So the question, is this just, or is it right that these transitions keep hurting the same vulnerable groups, the same indigenous communities, right, over and over again, entrenching elitism? That's not a question you can answer with economics. That's a moral question that demands that we grapple with ethics, social justice, equity, equality, gender, patriarchy, race. So again, a very interdisciplinary research agenda around those issues. Okay, to wrap it up. So to go all the way back to the beginning, we seem to have no shortage of definitions for energy transitions, and that also means that whether they're fast or slow gets you the prototypical it depends. It depends on how you define it. So whenever anyone is making a point about energy transitions, pay attention and think through energy, electricity, total primary energy supply, energy use. What is the unit of analysis? What assumptions? What thresholds? As well as what temporal or spatial dynamics? Are they thinking about coevolution? Are they thinking about mimicry? Are they thinking about phase out or just phase in? Also, going back to my expert elicitation exercise, we also have no shortage of tools. But in some ways, this is also kind of a minefield, right? Because imagine, 96 theories, and that's just, from a sample of 35 experts. Does that imply that none of them are any good, right? Like if we need to have, if there's 96 of them, does it mean none of them actually have strong resonance? There's no meta theory of transitions like there's Darwin's theory of evolution. Or is this good? This should be cherished. because it's a true sign of intellectual breadth, right? And if there are 96 ways to interpret a song, and 96 ways to interpret a film, and 96 ways to talk about love, well, then doesn't it make more sense? There's also 96 ways to talk about transitions, and that's just how it is. Humans are complex, intersubjective creatures. And we have a variety of useful tools that help us understand a phenomenon known as energy transitions. My own take is that all of them are useful. All of them bring something into focus, but also all of them also bring something out of focus, right? And so they're all useful, but all of them are also incomplete in their own way. So it kind of depends on fit for purpose with your research question and your type of case study selection and the type of analysis that you do. And the final thing that you can take away from the exercise is, at least at the time we did it, the two most hot, most frequently mentioned as useful theories were the multi-level perspective and social practice theory. And I can see NEST scholars like you kind of going two ways with this. On the one hand, I could say, ugh, if everyone's doing that, I'm not going to do it. I'll do something else. I could also see you saying, well, if those are the two that everyone seems to understand and expect, then there's a consensus, there's a norm, then these theories have utility and I should use them. And I will say we are probably getting at the journal that I edit a submission every other day that uses one of these two theories. Oh, this bullet point is out of order, but anyway, don't forget my point as well about how transitions, I think, require interdisciplinarity, whether you're trying to understand how to tweak, avoid, shift, improve across transport, buildings, food, industry. Whether you're trying to think about how to stimulate new cooking devices, right, that cuts across fuel science, buildings, gender. Whether you're thinking about how you're going to harness the MLP and try to understand culture and users and markets and discourses and power, which are all in modified versions of the framework. Or whether you want to also think through better issues of justice, which means perhaps engagement with the arts and humanities and ethics and philosophy. I think the causes of transitions are also complex. I didn't talk about this too much. In those fast transitions that I talked about, the 10 rapid ones, World War II had a huge role to play in the French nuclear rollout and the Kuwait push for oil and gas, because hostilities ceased in the Middle East. You could finally safely explore and extract oil. There was a rural famine behind the Chinese cook stoves program. The 1973 OPEC embargo had a huge role to play in both the Danish and Brazilian cases. The Brazilian case is a precursor, the pro-alcohol program is a precursor to their flex fuel program. Only one of the 10 was spontaneous demand driven, which was air conditioning, which is arguably the worst, right? Because it's actually not a net positive improvement for sustainability. This depressingly does suggest historical transitions are caused by war, famine, and crisis. And I really hope we don't need further future famines, wars, and crises to drive future transitions. But I'm somewhat hopeful because, as Florian and Carolina and Paula have said, well, future transitions can be different. We can actively govern them. We can phase out rather than phase in. And it could be that they're driven by scarcity rather than abundance or resource discoveries, or they're driven by changes in demand rather than a cessation in supply. Look at how fast we're trying to get off of Russian gas at the moment because of the Russia-Ukraine war. So all of this suggests to me that the past can be extremely instructive. So Grubler and Wilson and Nemeth and Smill are right. History does suggest slow transitions, but I still stand by the fact that they're not necessarily predictive, precisely because of the new drivers and dynamics that we've seen emerge in the past 10 years. So there is hope. And with that, I'll turn it back to Leo. Thank you for your time.